Welcome to the lecture series, What is Calculus? My name is David Britz. I'm an instructor of mathematics at Spokane Community College, and I'm making this set of videos because often in my algebra classes I get the question, when are we ever going to use this? A fair question, a great question, but not always answerable within a class period because it requires me to go into some terminology that we haven't discussed yet and takes up a lot of class time. So it's not something that's easy to answer during class. But at the same time, many of the basic ideas of calculus can be understood even as early as elementary algebra, or at SCC would be Math 91. So what I'm going to do in these videos, I want to explain some of the basic ideas of calculus, and I'm going to try to avoid as much as possible any calculus terms. So, in other words, this should be understandable. That's my goal, at least, is for this to be understandable to anyone who's completed elementary algebra, or in some cases intermediate algebra that might be more useful, but my goal is nothing more than an algebra background. So if you understand slopes, and if you understand the rate, time, distance formula, not necessarily the application problems. I know we do a lot of word problems in algebra with rate, time, and distance. That's not what I'm talking about here. I'm talking about just the idea of rate, time, and distance. And I'm going to cover these concepts in just a moment anyway. But so that's it. All you need is algebra, and let's get started. Okay, so what is calculus? And so we're going to start with a few concepts here. The first thing is velocity, time, and distance. So we know from algebra, we know that if we take the velocity and multiply by the time, we will get a distance. We often call this rate, but v times t equals d. So, for example, if you're traveling at 50 miles per hour for 2 hours, and the hours cancel and you get 100 miles. So that's really all we're talking about with velocity, time, and distance. So I'm not going to go any further than that. Just the idea of that equation, v times t equals d, that's what you need to know for now. And the other main idea from algebra is that of slope. So we know the slope formula. We've seen this often. And we talk about this as a change in quantities, right? So it's a change in y over a change in x. Okay. So now we got to put those two concepts together. So what I'm going to do then is I'm going to, instead of x, I'm going to let x equal time. And I'm going to convert y. Y is going to represent our distance. So let's rewrite the slope formula. So we have d2 minus d1 over t2 minus t1. And so what we have is we have a change in distance over a change in time. What do we call that? So, in other words, velocity, I'm going to say it's a type of slope. But velocity is a slope. It's how much does your distance change for a particular change in time. If your distance changes a lot, if d2 minus d1 is a large number, you have a high velocity. If your distance doesn't change that much, the numerator is going to be small and you're going to have a slow velocity. That's really all it is. So let's take an example here. Let's take an example where we have a velocity of 40 miles per hour and a constant velocity So let's look at this on a graph. And so let's say 0 hours, 1 hour, 2, 3, 4. So let this be time in hours. Let this be distance in miles. Let's kind of put a scale on this too, right? So let's go to all right, so after 0 hours, well, after 0 hours, we haven't gone anywhere yet. 1 hour, after 1 hour, we've gone 40 miles. After 2 hours, we've gone 80 miles. 3 hours, 120. 4 hours, 160. And so we can connect these basically in a straight line. So let's look at this for a moment in terms of the equation, right? Y equals mx plus b. There's our slope formula. Except we've changed x and y, right? So y is now the distance, m is a velocity, and x is a time. Now, what is the y-intercept? Well, the y-intercept is always going to be 0. We assume that if no time has passed, we haven't gone anywhere. So the y-intercept will just be 0, as you can see from the graph. And in our case, because velocity, we said the velocity is going to be 40, that's an equation. That's the equation of this line. And we see that the slope is 40 miles per hour. And the slope is constant because the velocity is constant. Okay? All right, so that's all fine and good, but of course, as we know, in real life, velocity is never constant. If everything in the universe moved at a constant velocity, well, life would be pretty boring, but we wouldn't, everything would be simple. Everything would be a linear equation, but of course, that's not the way life works. In the real world, velocity is not constant. Velocity changes. We speed up, we slow down, we accelerate, we decelerate. And so that's where things get a little bit more advanced. We're not at the calculus just yet. Everything I've done so far is stuff we do in every algebra class. So what my goal in this first lecture specifically is to kind of set up where we get into calculus. We're not doing anything with calculus just yet. Everything in this first lecture is all algebra, all review. But let's take another equation. Before we had d equals 40t, let's take this d equals 10t squared. So we're not going to have a constant velocity anymore. Let's do this over the same time period, right? So 0 hours, 1 hour, 2 hours, 3, 4. So, well, okay, after 0 hours we haven't gone anywhere. 10 times 1 squared, 10 times 1. We've done 10 miles. After 2 hours, 2 times 2 is 4. 10 times 4, 40. After 3 hours, 3 times 3, 9. So we've gone 90 miles. After 4 hours, 4 times 4 is 16, times 10 is 160. So that's all I'm doing here, is I'm just plugging values of t into our equation. So let's see what the graph of this would look like. So again, let's keep the same scale. And let's keep the same scale on the y-axis. So it's going to be 40, 80, and 160. Okay, so let's just going to plot the numbers here. They're no longer going to fall in a straight line. As you can see, we're accelerating. I'll get this as close as I can. It's not a straight line anymore. It's now curved because our velocity is changing. So, suppose we have the following problem. Okay, what is our velocity at 3 hours? Now, in the previous example, well, this was quite easy because the slope is 40 miles per hour. It's a constant speed, so if your average speed is 40 miles an hour, then 40 miles an hour is your speed at 0 hours, 1, 2, 3, 4, and everywhere in between, it's always 40 miles per hour. So it's an easy question to answer. Here, it's not so easy because the velocity is constantly changing. In fact, it's not as though you're going 30 miles an hour and then instantaneously you change to 40, and instantaneously you change to 60. That would be relatively easy as well. But the velocity, every single instant, not only does our distance change, but our velocity changes. So that's what makes this a little trickier. So I'm starting to kind of wrap up the first video. I'm going to get into the exactly how we find this in the next video. But I want to introduce some ideas first. I need to introduce a little bit of vocabulary. And for that, I think I'm going to redraw the graph because I want to exaggerate the curve a little bit. It's going to be easier to visualize. All right, so this is not to any particular scale. Let's just say here's 3 hours, here's 4 hours. I draw it this way to I want to exaggerate the curve a little bit because a lot of what I'm about to go into, it's going to be easier if we can make the curve seem steeper than it really is. So here's what we're looking for. If I want the velocity at 3 hours, another way of noting this is we want the slope of a line tangent. Tangent it's a fancy word. It just means that the line touches the curve in exactly one spot. It touches at 3. This is our end goal. This is what we are looking to find. That will give us our instantaneous velocity. Spell. That's what we're looking for. We want to find the instantaneous velocity. That's going to be the slope of the tangent line at t equals 3. Now, you may have noticed a problem. Why can't we find the slope at t equals 3? Anyone got it yet? We only have 1 point. The slope formula requires 2 points, and all we have is this. So that absolutely presents a problem. How can I find the slope of a line when we're given only 1 point? It turns out there is a way to do it, and I'm going to get into that method in the next video. But for the time being, let's present an alternative scenario. So instead of the instantaneous velocity, let's draw a line connecting 3 and 4. You can see this is why I wanted to redraw the graph. I just needed to exaggerate. This difference would not be as apparent on the other graph. So we call this, the instantaneous velocity, we call that the tangent line. And this average velocity, there's a name for this, it's called the secant. Again, these are fancy terminologies, but that's basically what we're doing. The secant line is going to give us the average velocity. So let's try to find that. Let's try to find the average velocity. Okay, well we could certainly do that. I mean, now we have 2 points, right? So from 3 to 4 hours, well, okay, so T1 is 3 hours, T2 is 4 hours, and at 3 hours, I believe that was 90 miles. Yeah, oh, it's right up there. Yeah. And after 4 hours is 160. So we divide the two, and we get 70 miles per hour. Okay, that's fine, but it doesn't answer our question. When you look at the speedometer of your car, you don't want to know how far what your average speed was in the previous hour, or the previous 10 minutes, or even the previous 5 minutes. You look at the speedometer of your car, you want to know how fast am I going right now. We want the instantaneous velocity. What we've got here is only the average velocity. It's not the instantaneous velocity at 3 hours, it's the average velocity between 3 and 4. They're two different things. However, this provides the setup. There is a way to find the instantaneous velocity. This is our first step. First, we want to find the average velocity, and then we can kind of take this a little bit further, and in the next video, I will show you how we can use these same concepts to actually find the slope of this tangent line with only 1 point. And I'll see you then. Thanks for watching.